Welcome to the Vibe Coders Manual, Episode 4, brought to you by AI, backed by lots of research how you turn Vibe revenue into real revenue.
Glad to be here for this one.
Yeah, so let's transition right into today's mission, which is zeroing in on a topic that, frankly, terrifies a lot of people.
Back-end architecture.
Exactly. Back-end architecture for solo founders. We are setting the stage in a fascinating and honestly somewhat treacherous era right now.
It really is. It's 2026, and the landscape has completely shifted.
Right. The modern solo developer's dilemma is totally unique compared to even just 3 years ago. Tools like Claude Code, Cursor, and V0 make it dangerously, deceptively easy to vibe code a working application for 50 users.
Oh, absolutely. You can literally prompt your way to a beautiful, highly functional front end in a single afternoon.
Yeah, you get that dopamine hit, you launch, and you feel invincible. But the brutal reality of the research we are looking at today is this. The back-end decisions you make in week 1, those quick choices you make just to get the app running and satisfy the compiler, are the exact same ones you are going to live with when you hit 1,000 users.
And usually, right around the 500 user mark, things quietly, invisibly, and systematically start to break.
They really do.
And that's exactly the core mission of this deep dive. We need to explore the architecture choices that actually compound in a solo founder's favor. But more importantly, we are going to call out the specific anti-patterns, the traps that lead to expensive, soul-crushing rewrites.
Yeah, because knowledge is most valuable when understood and applied, and right now, the sheer ease of front-end generation is masking massive back-end fragility.
Exactly. If you are building with AI today, you are generating technical debt at light speed unless you have a foundational architecture that can absorb it. The speed of creation has outpaced the speed of architectural comprehension.
And that's exactly why we are doing a vibe check right at the top. We are setting the tone as two technical founders, talking honestly about the mistakes we have seen in the trenches. We are skipping the generic startup advice.
Yeah, no fluffy listicles here.
Right. If you want a fluffy listicle about hustle culture, this isn't it. We are bringing concrete numbers, real trade-offs, and highly practical systems for developers who are stepping into back-end engineering at scale for the first time.
Which is a huge transition.
It is. So if you're sitting there right now building your SaaS, this deep dive is curated specifically to help you avoid the technical debt that outright kills early-stage products before they ever get a chance to thrive. We are going to look at the math, the memory limits, and the exact tools that give a solo developer the leverage of an entire engineering team.
Precisely. The barrier to entry for building software has functionally vanished, but the barrier to scaling it has not budged an inch. Scaling still requires physics, it requires memory, and it requires sound architectural logic. Let's start by dissecting what actually causes these early-stage systems to collapse under their own weight. The sources point to 3 specific architectural sins that consistently force founders into massive 6-month rewrites.
Okay, let's unpack this. The first sin mentioned in the research is the microservices complexity trap.
Yes, the classic trap.
Now, I want to push back on this right away because if you read any major engineering blog right now, or if you look at how Netflix, Uber, or Airbnb scaled, they all preach the gospel of microservices.
Right, they break everything down into tiny, independent, deployable units.
Yeah, and a lot of junior developers or founders just getting their footing look at those massive unicorns and think scaling inherently means splitting everything up right out of the gate. If I want to be a big company, shouldn't I build like a big company from day one?
It is a very seductive idea, but it is a massive trap for a solo founder. You are not Netflix, and attempting to mimic their organizational structure in your code base will destroy your velocity.
Because of the operational overhead.
Exactly. What's fascinating here is how the math of microservices strictly works against the solo developer. Let's run the numbers on a seemingly successful launch.
Okay, lay it out.
Imagine you build your system, you get featured somewhere, and you successfully hit 1,000 concurrent users. In a traditional, well-structured monolithic architecture where all your code lives in one application and talks to one database that is 1,000 incoming connections.
Which is highly manageable.
Very manageable.
Yeah.
But now, let's look at that same traffic through the lens of a microservices architecture. Your front end sends a request to your API gateway.
Okay, that's one hop.
Right. The gateway routes it to a user service. The user service has to verify the session token, so it makes a network call to an authentication service.
That's 3.
The auth service validates it and replies. The user service needs data, so it makes a network call to a profile service, which finally queries the database. Suddenly, one single user request has generated 4 to 6 internal service-to-service calls.
Wow. Right, so you haven't just scaled your user base. You have exponentially scaled your internal traffic. Your 1,000 concurrent users instantly become 6,000 concurrent network connections, firing back and forth inside your own infrastructure.
Exactly. And network calls are not free. Every single one of those hops introduces latency. It introduces serialization and deserialization overhead.
Just wrapping and unwrapping JSON constantly.
Yes. But more critically for the solo founder, it introduces multiple new failure points. If the authentication service container restarts, the entire chain fails.
And the user just gets a generic error.
Right. According to the internal data from developers and cloud architects in our sources, 65% of enterprise SaaS failures in the first 3 years are directly linked to infrastructure sprawl.
65%, that's massive.
And this sprawl is almost always caused by the premature fracturing of the architecture.
I can't even imagine being a team of one trying to debug that. A user submits a support ticket saying their profile picture isn't loading.
Good luck finding out why.
Right. In a monolith, you check the profile controller. In this microservices setup, you are searching through distributed trace logs across an API gateway, a user service, an image processing service, and an object storage service, all running in different containers. You'd spend your entire week just trying to find the line of code that threw the error.
Which is exactly why your feature velocity drops to 0. You stop building your product and you start managing infrastructure. For a solo founder, a well-configured monolith is almost always the right call.
Keep it simple.
Keep everything in one place, in one code base, deployed to one server environment. You only break a specific service out when the sheer compute volume of that one specific workload threatens to take down the rest of the application.
Like what? What's an example?
For example, if you add a heavy AI video rendering feature, that's a huge CPU drain. Until then, keep it together.
Okay, so if we accept the monolith, the next logical question is how big of a server do we need to run it? Because that leads us right into the second sin from the research, which is the memory and connection limit reality.
This one catches everyone off guard.
Yeah, I've noticed a trend where founders think their app is infinitely scalable because they used modern frameworks, but they are totally ignoring the actual physics of their servers. Most systems that founders think are scalable can't actually handle 100 real concurrent users clicking buttons at the exact same time.
This is a harsh reality check, and it requires us to dive into memory consumption. Let's look at dynamic languages like Python or Ruby, which are incredibly popular for rapidly building out SaaS backends.
Django, Rails, that sort of thing?
Exactly. A very common pattern in these frameworks is to load entire deeply nested user objects into memory just to process a single request. An ORM might pull the user, their settings, their organization, and their recent activity all into RAM at once.
Even if you only needed their email address for that specific route.
Yes. A single worker process doing this might consume 50 megabytes to 100 megabytes of memory.
Which doesn't sound like a lot in a world where laptops have 32 gigs of RAM.
It doesn't, until you do the math on a standard, affordable production server. Let's say you provision an 8 gigabyte virtual machine for your backend.
Pretty standard size for a new project.
Right. If the operating system and background tasks take up 2 gigabytes, you have 6 gigabytes left for your application. If each concurrent user request requires its own worker process holding 100 megabytes of RAM, you're going to hit a hard mathematical limit at about 60 concurrent requests.
Only 60.
Maybe you optimize a bit and get it to 100 or 150, but you hit a solid brick wall far earlier than you'd expect.
And what actually happens when you hit that wall? Because it's not like the server politely asks the 101st user to wait in line. It's not a graceful degradation.
Not at all. This raises an important question. What does server death actually look like? When the server runs entirely out of RAM, the operating system panics.
It just freaks out.
To prevent a total crash, it starts swapping memory to disk. It takes the data currently in RAM and aggressively writes it to the hard drive to free up space and then reads it back when needed.
And hard drives are slow.
Even if you are using high-end NVMe SSDs, a hard drive is orders of magnitude slower than actual RAM. The moment your server starts swamping, your application's response times collapse.
Like how bad?
A request that took 40 milliseconds suddenly takes 15 seconds.
Oh, wow.
Then, the incoming requests start piling up faster than the swapping server can clear them. Connection pools max out. CPU spikes to 100%, just managing the memory swapping overhead. And eventually, the server just becomes entirely unresponsive and drops all connections.
Which means your users are staring at endless loading spinners until they eventually get a 502 bad gateway error. It's a terrifying thought experiment for anyone who hasn't actually load tested their MVP. We all test our apps by clicking around ourselves, maybe opening 2 browser windows.
Right, which proves nothing about scale.
Exactly, but the research is begging us to ask you, if you ran a load test right now, say 10,000 requests with 1,000 concurrent connections, would your system survive or would it instantly fold? Because most MVP systems are strictly optimized for demo traffic, not production load.
And when founders hit these memory limits, when the app inevitably crashes under a totally modest traffic spike, they panic.
They completely lose it.
They don't look at their ORM queries or their memory footprint. Instead, they commit the third architectural sin, the Big Bang rewrite fallacy.
It's my favorite one to hate.
They convince themselves that their initial architecture is fundamentally flawed garbage, and the only solution is to throw it all away and start from scratch in a faster language like Rust or Go.
Yes, the classic, we just need to rewrite the whole thing, delusion. The sources bring up some incredible canonical disasters in software history regarding this, specifically Netscape in 1998.
A perfect example.
They had a working dominant web browser, but the code was messy. So they decided to freeze feature development and rewrite the browser entirely from scratch.
And what happened?
The result was a massive 3-year delay where they shipped absolutely nothing of value to their users. And during that window, Microsoft's Internet Explorer completely took over the market and essentially killed the company.
The Netscape example is the ultimate cautionary tale of what Fred Brooks called the second system trap way back in 1975.
It's been a known issue for 50 years.
Exactly.
Yeah.
When developers build a second system, they try to over-engineer it. They try to cram in every feature they couldn't fit into the first one, and they dramatically, fatally underestimate the value of the old, existing code. Founders look at their legacy code and think it's just a messy, embarrassing spaghetti pile.
Because it usually is messy.
It is, but legacy code is really just code without tests that happens to contain years of hard-won edge case handling.
I love that framing. Those weird, ugly conditional statements in your code base, the ones you hate looking at, they don't exist because you were a bad coder. They exist because a user did something wildly unpredictable 2 years ago, the app broke, and you had to patch it.
Exactly. When you rewrite from scratch, you intentionally throw away all that institutional knowledge. You are arrogant enough to believe you won't make those mistakes again, but in reality, you just have to rediscover every single edge case the hard way, usually by breaking the application for your existing users.
So what is the pragmatic alternative for a solo founder who genuinely has outgrown their initial messy code? Let's say the technical debt is legitimately dragging them down. How do we incrementally fix it instead of doing these massive 6-month feature freeze rewrites where the business essentially stalls out?
The industry gold standard highlighted in the research is the strangler fig pattern.
Like the plant.
Yes, it's named after a type of vine that slowly grows over an existing tree, taking root and eventually replacing the host tree entirely.
That's a great visual.
Instead of rewriting everything in a dark room for 6 months, you replace it piece by piece, route by route, while the legacy system is still running in production. Let's contrast Netscape with Twitter. In the early days, Twitter's Ruby on Rails backend was famous for buckling under scale. We all remember the fail whale graphic.
Oh yeah, seeing that whale meant Twitter was down again.
But they didn't shut down for a year to rewrite the whole platform. They kept the fight running while they took 5 years to incrementally replace components, carefully moving the heaviest workloads to Scala and Java microservices one piece at a time.
Or look at Stripe. The sources mention that Stripe uses what are arguably ugly, deeply complex compatibility layers in their codebase.
They absolutely do.
But those layers serve a massive business purpose. They allow Stripe to keep shipping brand new features on modern architecture without ever breaking existing, older integrations for their legacy customers. They refuse to break backward compatibility, even if it makes the internal code less pure.
And that is the crucial mindset shift. You do not freeze your business to fix your code. You fix your code while running your business. A solo founder's only real advantage against larger competitors is momentum. The moment you stop shipping features to embark on a massive rewrite, you surrender that momentum.
Okay, let's synthesize this first part. To survive the journey to 1,000 users, we avoid microservices and build a monolith. We strictly monitor our memory footprint per request so we don't hit the swapping wall. And if we do need to refactor, we do it incrementally using the strangler fig pattern.
That's the survival guide right there.
But assuming we follow these rules, we still have to actually put this code somewhere on the internet. Where do we host this monolith? The hosting landscape right now is incredibly fragmented. The sources dive deep into the concrete numbers here, so let's look at the serverless versus always-on trade-offs.
This is where the budget actually gets decided.
Let's start with the absolute dominant force in the front-end world right now, the Vercel and serverless ecosystem.
Vercel has achieved near absolute dominance for Next.js applications and modern React front ends. Their fluid compute model is objectively highly sophisticated. What they've done is bring traditional auto-scaling concepts to serverless infrastructure, extending it to run function invocations concurrently.
Meaning they handle spikes really well.
Extremely well. This means you are theoretically only charged for active CPU time while a request is processing, not for idle time when the server is just waiting for traffic. Furthermore, the developer experience is incredibly streamlined, from a simple Git push to a globally deployed CDN-backed application in seconds.
But there is always a catch, right? Especially for solo founders who are bootstrapping and trying to maintain highly predictable profit margins. The Vercel pricing model has some very specific pain points hidden in the fine print.
There is a significant catch, and it's twofold. First, Vercel operates on a tiered subscription model with a heavy per-seat tax. Once your project moves off the restrictive hobby tier, which you must do for any real commercial venture, it costs $20 per user per month just for the base access before you even factor in heavy compute costs.
And as a solo founder, you're eating that seat cost.
Yes, but the more architectural restriction is the hard execution limits of serverless functions.
Right, because a serverless function isn't a persistent server. It spins up, does its job, and dies.
Precisely. On a Vercel hobby plan, a serverless function will strictly time out and kill your process after 10 seconds. On a paid pro plan, that limit extends to 60 seconds.
Which is still incredibly short for back-end tasks.
It is. This architectural constraint means you fundamentally cannot run persistent back-end services on this platform. If you want to build a real-time chat application, you cannot run a long-lived WebSocket server here because the connection will be violently severed after a minute.
Just completely cut off.
Yes. You cannot run heavy background workers or cron jobs that take 3 minutes to process a video or generate a large PDF. Serverless is amazing for variable, unpredictable front-end traffic-serving HTML and quick API JSON responses, but it entirely falls apart when you need persistent, stateful back-end plumbing.
Which forces a lot of developers to look for alternative hosting models. And that brings us to a wildly different approach mentioned in the research Railway. I'd call this the full-stack container simplicity approach.
Railway has a very different philosophy.
They don't force you into serverless functions. They offer usage-based pricing, and they actually run their infrastructure on their own hardware, which they call Railway Metal. This means you can deploy a standard, always-on Docker container. You can have your Next.js app, your Postgres database, and your Redis instance all running natively in one beautifully unified project UI.
The developer experience of Railway is fantastic, but let's crunch the actual numbers, because the usage-based model completely changes the financial math for a solo founder. Railway is incredibly cheap for highly variable, low-traffic workloads, specifically because of their scale-to-zero feature.
How does that work in practice?
If you have a weekend side project that only gets traffic for a few hours a day, Railway will literally spin the compute container down to zero when it's idle. You aren't paying for empty servers. In that scenario, your monthly bill might only be $5 to $10.
But what happens when the app actually succeeds? What happens when you have users across different time zones and the app can never scale to zero?
That is where the pricing curve gets steep. If your SaaS takes off and you need an always-on, medium-sized virtual machine to handle constant traffic, say a server with 4 vCPUs and 8 gigabytes of RAM, you are looking at approximately $160 per month on Railway.
Just for that one server?
Yes. That is the premium you pay for their beautiful interface and having your database, cache, and compute managed in one single dashboard.
And $160 a month is a real line item for a bootstrapped solo founder. If you're running 3 micro-SaaS projects, you're suddenly burning $500 a month just to keep the lights on. So the sources bring up a major disruptor to this pricing model, the Fly.io alternative. They take a totally different path by utilizing global edge VMs, specifically technology called Firecracker micro VMs.
If we connect this to the bigger picture of raw compute economics, Fly.io is incredibly disruptive. They have stripped away the premium UI overhead and focus purely on providing raw, highly efficient compute. Let's look at the exact same server specs.
Okay, let's compare them directly.
On Fly.io, a small VM with 1 vCPU and 2 gigabytes of RAM is about $10.70 a month. But let's look at the medium VM, the main 4 vCPU and 8 gigabytes of RAM machine that we just priced at $160 on Railway.
Right.
On Fly.io, that exact same compute power is only about $42.79 a month.
That is wild. That is nearly 4 times cheaper for always-on persistent workloads. The real takeaway from the research isn't just that Fly.io saves you $120 a month. It's that it fundamentally alters your business model.
In what way?
At $42 a month for an always-on server, a solo founder can afford to offer a generous freemium tier that a Vercel-bound or Railway-bound competitor literally cannot afford to match. You have a massive structural cost advantage, and the bandwidth costs compound that advantage, right?
Absolutely. Bandwidth or data egress is the silent killer of cloud budgets. Fly.io gives you 100 gigabytes of free egress bandwidth per month and only charges 2 cents per gigabyte after that.
2 cents?
Yes. To put that in perspective, compare it to Vercel, which charges a staggering 15 cents per gigabyte at the edge, or Railway's 5 cents. If your application serves a lot of heavy data, like high-resolution images, audio files, or dense data exports, hosting on Fly.io will save you an absolute fortune as you scale.
And Fly.io has another massive architectural advantage for founders operating in 2026 GPU access.
This is critical now.
We're in the AI era. If you are building complex AI workloads, you eventually hit a point where third-party APIs aren't enough, or they are too expensive. You need raw access to hardware like the A10, A100, or L40S chips to run custom machine learning models, like an open-source Llama model or a specialized voice transcription service. Serverless front-end platforms like Vercel fundamentally lack this native, heavy-duty GPU access. Fly.io lets you attach a dedicated GPU to your VM and pay by the hour.
Exactly. It gives the solo founder enterprise-level infrastructure capabilities.
Right.
But as with all things in engineering, Fly.io comes with a distinct trade-off in developer experience.
There's always a trade-off.
You don't just click a button and deploy. You have to understand and write fly.tom LML configuration files. You are responsible for managing persistent virtual machines, health checks, and load balancing. And unlike Railway, there is no built-in managed Redis database you can just toggle on. It requires significantly more operational overhead and Linux knowledge.
So, if we synthesize this compute decision matrix for the listener, use Vercel if you are building an entirely stateless front-end or static site and want the absolute best delivery experience. Use Railway for rapid full-stack prototyping, where you prioritize development speed and want your database and compute in one unified UI, and you don't mind paying a premium as traffic grows. But use Fly.io when you have steady, always-on traffic, high bandwidth needs, require GPU access, and want the absolute lowest cost for raw compute power.
That is an accurate assessment of the compute layer. But compute is only half the equation. A powerful backend server is completely useless if the data layer beneath it bottlenecks. The state of your application, your actual data, is the most critical asset you have.
Which transitions us perfectly into the database landscape. The research points out a fascinating divide here when it comes to storing data for these solo projects. We're going to look at concrete pricing and hard limits for the big 4 databases dominating the solo founder stack in 2026.
Let's start with the big one.
First up is what the sources call the backend-in-a-box Supabase. I have to admit, I look at Supabase and it really feels like the ultimate shortcut for a solo founder. It is staggering what they give you. You get a full Postgres database, a complete authentication system, AWS S3 compatible object storage, edge functions, and real-time WebSockets, all bundled into one massive open source platform.
It is an incredibly powerful, cohesive ecosystem. But we need to break down the pricing mechanics because it scales very differently than usage-based models.
Let's hear the numbers.
The Supabase free plan is phenomenally generous for an MVP or a prototype. You get a 500 megabyte database, 1 gigabyte of file storage, and up to 50,000 monthly active users for auth. However, the moment you move to a production application, you must upgrade to the Pro plan, which starts at $25 per month.
Right, and $25 a month is basically nothing for a successful business. But there is a structural detail here that solo founders miss.
The critical detail is that Supabase uses dedicated database instances. This means they spin up a specific virtual machine solely for your database.
Yeah.
Because of that, you pay that $25 a month flat fee, even if your application gets absolutely zero traffic.
Oh, right, because that server's just sitting there.
Exactly. For a single production app, $25 is negligible. But solo founders rarely have just one app. If you are running 5 different micro SaaS projects or side bets, that is $125 a month in fixed, unyielding costs before you even acquire a single paying user. Furthermore, if your application grows and you need high availability, say, a setup with a primary database node and 2 read replicas to ensure the system never goes down, a comparable high availability Supabase setup with high IOPS storage can exceed $2,100 a month.
Now that $2,100 a month figure is suddenly enterprise territory. It's a massive cliff. So what if I want to keep my costs directly tied to my actual usage? I don't want to pay for idle time, and I want a smoother scaling curve. That brings us to the second option in the research, the serverless innovator, Neon.
Neon fundamentally reimagines how Postgres operates. They have architecturally separated the storage layer from the compute layer.
Wait, how does that work?
In a traditional database, the hard drive storing the data and the CPU processing the queries are physically tied to the same machine. Neon separates them over a network. This architectural choice enables true scale to zero for a relational database.
Which solves the exact problem we just talked about with Supabase's fixed costs.
Exactly. Neon's free tier gives you 100 compute unit hours per month. The entry plan is $19 a month, but it is purely usage-based, scaling at 14 cents per compute unit hour. Because the compute layer scales to zero when there are no queries, an idle side project might literally cost you $5 a month, entirely matching your traffic patterns.
Here's where it gets really interesting with Neon, though. Because they separated storage from compute, they unlocked a feature that feels like magic for developers' database branching. Let's walk through how this actually works mechanically.
Neon uses a copy-on-write mechanism at the storage layer. If you want to clone a 100-gigabyte database, a traditional provider would have to physically copy 100 gigabytes of data to a new server.
Which takes hours and doubles your storage costs.
Right. Neon doesn't copy the data. It simply creates a pointer to the existing storage snapshot.
So it's instant.
The new branch only stores the delta, the new data written specifically to that branch.
This is a total game changer for developer workflows. Let's say you are a solo founder working on a massive new feature that requires a risky database schema change, like dropping a table and merging 2 others. On Neon, creating an isolated branch of your production database for your pull request takes milliseconds and costs almost nothing. You run your tests against real production data, verify the migration works, and then confidently deploy.
It's incredibly safe.
Supabase, by contrast, requires provisioning a completely new dedicated database instance and running all your migrations from scratch to spin up a testing branch, which is much slower and consumes compute credits. Neon integrates flawlessly into a Vercel deployment pipeline, automatically giving you a fresh, isolated database branch for every single preview URL generated by a Git push.
It's a huge workflow advantage.
Okay, so Supabase is the full toolkit, and Neon is the serverless branching king. But what if I am building something where the data is absolutely mission critical, like a fintech app or a healthcare portal? What if I just want pure, unbreakable reliability above all else?
That's where the third option comes in. PlanetScale.
Right. The research notes it's built on Vice, which is the exact technology YouTube developed internally to scale their massive databases. They originally focused exclusively on MySQL, but now they offer Postgres compatibility via a system called Nike.
PlanetScale is the pure database reliability play. They aren't trying to offer auth or edge functions. They focus entirely on managing massive data volume at scale. The defining features of Vice are horizontal sharding and non-blocking schema changes.
Let's unpack that jargon. What does horizontal sharding actually mean for a solo dev?
Sharding is when a database gets so impossibly large that it cannot fit on a single physical hard drive, so you have to split the data across multiple servers. Doing this manually is an operational nightmare. You have to write complex application logic to know which server holds which user's data. Vice handles all of this under the hood.
So the developer doesn't even see it.
To your application, it looks like one single database. But Vice is quietly routing queries across dozens of underlying servers. And non-blocking schema changes mean you can add columns or modify massive tables with millions of rows without locking the database and taking your application offline.
But this reliability comes at a premium, right? PlanetScale got rid of their free tier entirely.
Correct. There is no more free tier. It starts at a $5 a month scaler plan. But let's go back to that high availability benchmark we use for Supabase. Remember the 2,100 a month figure?
Yeah, the enterprise cliff.
A 3-node PlanetScale M320 high availability setup costs $1,349 per month. Compared to Supabase, PlanetScale offers incredible performance and bulletproof reliability at a significantly lower cost for applications that demand strict high availability and zero downtime schema migrations. If your app simply cannot afford to go offline during a database update, PlanetScale is the gold standard.
Finally, we have to mention the wildcard in the research, the edge specialist Turso. Turso takes SQLite, which is traditionally just a local file-based database, and distributes it globally using a fork called libswell. This is a completely different mental model from heavy centralized Postgres databases.
Turso is built for very specific architectural needs. SQLite is incredibly fast, but typically only lives on one machine. Turso takes that database file and replicates it to edge locations all over the world.
What kind of app needs that?
If your application is incredibly read-heavy, say, a content directory, a global product catalog, or a configuration service where 90% of the operations are reads and 10% are writes, Turso shines. Because the database is physically distributed to edge servers in London, Tokyo, and New York, close to the end users, you can achieve sub-10 millisecond query latency globally. It is also phenomenal for building mobile applications that require offline-first capabilities, allowing the app to sync a local SQLite database with the global edge database seamlessly.
If you're sitting there right now trying to pick your stack, the research essentially draws this map. Go with Supabase if you want the entire back-end infrastructure auth storage database handed to you on a silver platter, and don't mind the fixed $25 base cost. Choose Neon if you are heavily integrated into Vercel, have intermittent traffic, and want the workflow magic of database branching. Choose PlanetScale if you're building mission-critical software that requires pure database reliability and safe, non-blocking schema changes. And choose Turso if you need lightning-fast reads distributed globally to the edge.
That perfectly synthesizes the database landscape. However, once you choose your database, you face the next massive architectural hurdle. When you successfully hit 1,000 users, or 1,000 different companies using your B2B SaaS, how do you keep their data strictly separate and secure? You're putting everyone's highly sensitive information into the same database.
And this is the stuff that should keep founders awake at night. This is where companies die. If you have 1,000 different companies on your app and a bug in your code accidentally shows company A's financial data to company B, your business is instantly dead. You lose all trust, and you're likely facing legal action. So how do we architect this isolation? We essentially have two paths, according to the research, the pool model versus the silo model.
Let's outline the spectrum of isolation. The silo pattern, which is a strictly database per tenant architecture, offers maximum physical security. Every single customer gets their own completely separate database instance. The data is physically walled off.
Which sounds great for security, but the operational overhead seems impossible for a solo developer.
It is entirely impossible for a solo founder. If you have 1,000 customers, you have 1,000 distinct databases. When you want to push a new feature that requires adding a single column to a table, you have to write a script that connects to 1,000 separate databases and runs 1,000 separate schema migrations.
And things will fail.
Constantly. If migration number 412 fails due to a network timeout, your fleet is out of sync. Some customers have the new feature, some don't. It is an unmanageable nightmare unless you have a dedicated DevSecOps team and are charging astronomical enterprise fees to justify the overhead.
Right, so the silo model is definitively out for the solo dev. That means we have to lean into the pool pattern. This is a single shared database with a shared schema. All 1,000 customers are in the same users table, the same orders table. Every table just has a tenant ID or organization ID column. It's the gold standard for solo founders because it is incredibly resource efficient. You run one migration and everyone gets the update. But it is terrifyingly risky if you just rely on your application code to say where tenant ID equals X. If you are tired and you forget that where clause in just one API route out of 100, you instantly leak data to the wrong user.
Exactly. Relying solely on application-level filtering, trusting that your ORM queries are perfectly written every single time, is a recipe for a catastrophic data breach.
No.
Human error is inevitable. The concrete strategy highlighted in the sources to mitigate this risk is to enforce isolation at the database level itself, using a post-RESTful feature called row-level security, or RLS.
Let's break down exactly how RLS prevents those application layer leaks, because this is a crucial concept.
With RLS, you define security policies directly inside Postgres. You instruct the database engine. Do not allow any row to be read or modified. unless it belongs to the current user. But how does the database know who the current user is? You set a session variable, something like app.currentTenantID, via your connection pooler at the very start of the transaction before any queries are run.
So the database itself acts as the final gatekeeper.
Exactly. Even if your application code is flawed, even if a junior developer or an AI coding assistant generates a naked select star from orders query and forgets the where clause, the database will intercept the query. The Postgres engine will dynamically apply the RLS policy, check the session variable, and only return the specific rows where the tenant ID matches. It mathematically protects you from your own coding mistakes. The data leak becomes impossible at the database layer.
That is bulletproof architecture. But mentioning connection poolers brings up the second half of this data section. We touched on this briefly during the serverless versus always-on debate. If you are using serverless functions on Vercel or Neon, those functions spin up, open a database connection, do one quick task, and immediately die. They do this hundreds or thousands of times a second under load. If they connect directly to Postgres, the database crashes instantly. Why?
Because Postgres was designed decades ago for a world of long-lived, persistent connections. Every time a client connects directly to Postgres, the database engine creates a brand new, heavy operating system process, allocating significant memory to handle that specific connection. Postgres cannot physically handle thousands of rapid open and close requests per second. It exhausts the service process limits in memory instantly. Therefore, if you're using serverless compute, you must put a connection pooler between your app and the database.
Think of PostgreSQL like an exclusive, high-end restaurant where every single guest gets their own dedicated waiter. If 1,000 people rush the door at the exact same time, the restaurant goes bankrupt, trying to hire 1,000 waiters on the spot. A connection pooler acts as a highly efficient host at the front door. The host happily takes orders from all 1,000 people, but only sends 40 waiters into the kitchen to process those orders as fast as they can.
That is a perfect analogy. Neon solves this beautifully by bypassing standard TCP connections entirely. They offer a native WebSocket serverless driver, which is incredibly lightweight. Supabase uses a system called Supervisor, which is a pooler based on the industry standard PgBouncer. Supervisor is incredibly robust. In benchmark tests, it has successfully triaged 1 million concurrent incoming client connections down to just 400 actual heavy database connections without crashing. It is the ultimate waiting room for your database.
But there is a massive silent danger zone here, specifically for developers using modern ORMs like Prisma or Drizzle. This is a trap that can literally break your app instantly, and it causes endless frustration on developer forums.
Yes, I want to issue a strict warning here based on the research. When you configure a pooler like PgBouncer or Supervisor, you typically set it to transaction mode. This mode is highly efficient. It rotates the actual back-end database connections between different client queries rapidly. However, modern ORMs like Prisma and Drizzle often use a PostgreSQL feature called prepared statements under the hood to speed up query execution times.
Let's clarify that. A prepared statement is essentially the database pre-compiling a query, right? And critically, that prepared statement is strictly tied to a specific database connection.
Exactly. It caches the execution plan on that specific connection. Here's where the fatal conflict occurs. Imagine client 1 sends a query. The pooler hands it to connection A. Connection A creates a prepared statement. Client 1 finishes. Now client 2 sends the exact same query. The pooler, operating in transaction mode, routes client 2's query to connection B. Connection B looks for the prepared statement, but it doesn't exist on this connection. It only existed on connection A. The database throws an error, the query fails immediately, and your application crashes. You are essentially talking to a stranger, expecting them to remember a conversation you had with their colleague.
Here is where it gets incredibly practical, because the fix is so ridiculously simple, but if you don't know it, you will waste weeks debugging. How do we fix this prepared statement conflict?
You must explicitly tell your ORM not to use prepared statements when it is routing traffic through a transaction mode pooler. For Prisma, you simply append the string $PgBouncer equals true to the very end of your database connection URL string. That one flag alters Prisma's behavior globally. For Drizzle, you must configure the connection object and explicitly set prepare :false.
It is wild that appending $PgBouncer equals true to a URL is the literal difference between a highly scalable application and a completely broken crash looping mess. This is exactly the kind of unglamorous technical plumbing solo founders need to understand.
Furthermore, as a general rule regarding connection pools, the sources advise keeping your pooler usage under 40% of the database's maximum available connections. If your Postgres server allows 100 maximum connections, Configure PgBouncer to only use 40. Why? Because if you allow your external web traffic to consume 100% of the connections, you will completely starve your internal platform services. Services like Supabase's off microservice or their real-time WebSocket servers need their own connections to verify tokens and stream data. If your web app hogs all 100 connections, the auth server can't talk to the database, users can't log in, and the entire back-end system freezes in a deadlock.
Okay, so we've established a rock-solid foundation. We have our database secured with RLS, we have our connection pooler perfectly tuned to avoid prepared statement crashes, and our compute is running efficiently. But if we are building a SaaS in 2026, we aren't just doing basic CRUD operations anymore, we are talking to LLMs, which transitions us to a massive pain point in modern architecture async job queues for AI workloads. The world completely changed with the integration of AI, and traditional queuing systems are violently breaking under the pressure.
The architecture required for AI is fundamentally different. In 2026, AI integrations are rarely simple sub-second API calls. They are complex, long-running, multi-step operations. Let's walk through a concrete scenario. You are building an AI agent that reviews legal contracts. A user uploads a 50-page PDF. Your system needs to parse the PDF, chunk the text, send those chunks to an embedding model, store them in a vector database, then construct a complex prompt, pass that context to an LLM like GPT-4 or Claude, wait for the generation, and finally email a summary to the user. This entire process can take 5 to 10 minutes. Furthermore, it is highly susceptible to unpredictable API rate limits from those providers. If OpenAI returns a 429 too many requests error on minute 4, what does your system do?
And this is exactly where traditional infrastructure dies. If you try to run that 10-minute process on AWS Lambda, the Lambda function hits its hard 15-minute execution limit, and the process is killed instantly. If you run it on Vercel, it dies in 60 seconds. So historically, developers would use background queues like Boolean queue running on Redis to handle long tasks. But those fail here too, right? Because they don't gracefully handle a multi-step process pausing for a rate limit without writing incredibly complex manual state management logic to track exactly which step failed and where to resume.
Exactly. Traditional queues are dumb. They just retry the whole job from the beginning. And the job fails at minute 9, it starts over at minute 1, wasting expensive LLM tokens. What modern AI applications require is a concept called durable execution. Durable execution means the workflow platform guarantees that the code will eventually finish executing, no matter what happens to the underlying server. It survives timeouts, server crashes, and prolonged rate limit pauses without losing its local state or restarting from the beginning. It picks up exactly where it left off, down to the specific line of code.
So who are the leaders in durable execution right now for solo founders? The research highlights 3 main contenders: Trigger.dev v4, Inngest, and render workflows. Let's start with Trigger.dev because their v4 update is a fascinating piece of engineering.
Trigger.dev v4 is a technical marvel. They have solved the durable execution problem by utilizing a deeply powerful Linux technology called CRIU, which stands for Checkpoint Restore in User Space. This is not a new web framework. This is a low-level Linux kernel tool that companies like Google use internally to migrate massive workloads across servers without dropping connections.
How does that apply to a developer writing a long-running AI function?
When your code hits a function like wait dot for 5 hours, or what Trigger calls a wait point, like waiting for an external API webhook to return the friend, Trigger.dev intercepts that command. It literally freezes the executing node.js container, captures the entire state of the RAM, and writes that memory state directly to the hard disk.
It literally freezes the RAM to the hard drive. It serializes the entire process memory so the server isn't actually running while it's waiting.
Precisely. Because it is frozen to disk, the compute is entirely suspended. You do not pay for idle compute time while waiting hours or even days for an event to resolve. When the wait is over or the webhook arrives, CRIU restores the container memory from the disk in just 100 to 300 milliseconds. This is a dramatically faster warm start compared to older serverless versions, and it resumes execution on the exact next line of code with all your variables perfectly intact. Their pricing model is also highly accessible for solo founders, ranging from a generous free tier up to $25 a month for substantial usage.
That is incredible infrastructure abstraction. Now, what about Inngest? They take a different architectural approach. They don't freeze containers. They embed their engine right into your existing code.
Inngest is fantastic for developer experience. It provides a TypeScript-first SDK that runs entirely inside your existing hosting environment, whether that's Vercel, Render, or Fly.io. You define your step.run, generate embeddings, step.run call, lm is men, and Inngest manages the state between those steps via HTTP calls. You don't have to provision or manage a separate worker environment. It uses your existing servers. However, the catch is the billing structure.
Let's unpack the billing, because that's always where the pain is hidden.
Inngest charges per step executed. Their base paid tier is $75 a month, which includes 1 million step runs. For simple tasks, this is completely fine. But consider the AI agent scenario we discussed. If your agent executes dozens of small steps, loops over document chunks, and relies heavily on automatic retries to handle rate limits, every single one of those actions counts as a step. If you have 1,000 users running complex agents daily, this step-based billing can scale wildly unpredictably. A $75 bill can very quickly become a $500 bill just from successful internal processing loops.
And lastly, the sources mention render workflows.
Render workflows takes a more infrastructure-centric approach. It allows you to convert your existing asynchronous functions into durable tasks simply by adding a specific decorator in your code. Because render provisions persistent, underlying infrastructure, these tasks can run for hours without the strict timeout constraints of pure serverless platforms like Vercel.
What's fascinating to me here is the sheer amount of operational burden these platforms have eliminated. 5 years ago, to build that AI contract reviewer, a solo founder would have to manually provision a Redis cluster, set up a dedicated pool of Celery or Sidekick workers, write custom dead letter queues to handle failed API calls, and build a database schema just to track the status of the job. Today, you just write normal asynchronous TypeScript code, wrap it in a Trigger.dev or Inngest function, and the platform mathematically guarantees it finishes. That is a massive superpower.
It truly is. It allows a single developer to orchestrate highly complex asynchronous systems that previously required a dedicated backend team. But running all these powerful abstracted systems, your branching Neon database, your Fly.io compute, your durable Trigger.dev workflows creates an entirely new, urgent problem. When something inevitably goes wrong, how do you actually know what's happening inside them? You have black boxes talking to black boxes. This brings us to the final piece of the architecture puzzle, minimum viable observability setup.
Observability. The land of massive enterprise tools like DataDog, New Relic, and Splunk. I always joke that installing DataDog without a dedicated DevOps engineer watching the billing dashboard is the fastest way to accidentally bankrupt an early-stage startup.
It is a common and very painful reality. DataDog is an undeniably powerful world-class platform, but its pricing matrix is incredibly complex. It charges per host, per gigabyte of data ingested, per million indexed events, and charges extra for custom metrics. When you have a modern architecture, especially one logging large JSON payloads from LLM responses or detailed trace data from your connection pooler, those dimensions multiply against each other. It creates shockingly high, entirely unpredictable bills. Solo founders do not need and cannot afford comprehensive enterprise observability suites. What they need is a minimum viable observability stack that provides immediate actionable insights without costing more than the application's hosting itself.
So let's build that exact stack for the listener right now. What tools do we use to monitor this infrastructure on a budget? Let's start with code health and error tracking. When the app throws a 500 error, where do we look? The undisputed king here, according to the sources, is Sentry.
Sentry remains the industry standard for code health for a very specific reason context. When a critical exception occurs in your application, Sentry doesn't just log a generic text message like error undefined variable. It captures the full exception, provides deeply detailed stack traces pointing to the exact file and line of code that failed, and captures the environment state, what browser the user was on, what OS, and what API parameters they passed.
And they have that incredible session replay feature now, right?
Yes, the session replays are invaluable. You can visually watch a video-like playback of the user's screen interactions in the exact moments leading up to the crash. You don't have to guess what they clicked, you watch them click it. This context reduces debugging time from hours to minutes. Sentry offers a very generous free tier of 5,000 recorded errors per month, and their base paid tier starts at a highly reasonable $26 a month.
But Sentry is strictly for exceptions and crashes. It isn't meant for dumping gigabytes of raw analytics, access logs, or the massive AI prompt logs we just talked about.
Yeah.
If you log every single LLM response into Sentry, you will blow through your 5,000 error quota in an hour. So for high-volume, structured logs, where do we turn?
For high-volume data, the research points strongly to Axiom. Axiom is perfectly positioned for the AI era. Modern applications generate terabytes of structured JSON logs. You want to log the exact prompt sent to OpenAI, the exact response, the token counts, the latency metrics, and user behavioral events. Axiom utilizes a custom serverless architecture specifically designed for 100% data retention without sampling data down. They achieve up to 95% data compression on ingestion.
And what does that compression mean for the price? Because DataDog charges a fortune for ingestion.
Because of that extreme efficiency, Axiom's pricing is incredibly disruptive. It starts at just $25 a month. More importantly, it operates without the variable, unpredictable query costs that plague legacy enterprise tools. You can query your terabytes of AI logs as often as you want without fear of a surprise bill. It is the perfect complement to Sentry. Use Sentry strictly for actionable exceptions and crashes, and use Axiom as your massive data lake for analyzing high-volume behavioral and system log data.
And to round out the stack, we need to know if the site is actually online. Because if fly.io goes down or the DNS fails, Sentry won't report errors because the site can't even load. For uptime, the sources recommend Better Stack.
Yes, Better Stack essentially replaces clunky legacy tools like PagerDuty and Pingdom. It offers an incredibly clean, unified interface for minute-by-minute uptime monitoring across different regions, incident alerting via SMS or phone calls, and highly polished public status pages for your users. It starts at a highly predictable $29 a month.
So let's do the math on that observability stack. You have Sentry for $26, Axiom for $25, and Better Stack for $29. For exactly $80 a month, a solo founder gets enterprise-grade visibility across code exceptions, high-volume AI logging, and global uptime alerting without the terrifying variable enterprise price tag. That is how you build leverage.
Exactly. It's about strategic tool selection, not blind adoption.
Yeah.
If we synthesize this entire deep dive, the overarching theme of the research is this: architecture isn't about perfectly guessing what you will need when you eventually hit 1 million users. It is about making pragmatic, calculated decisions today, avoiding the microservices trap, understanding the brutal math of memory limits, utilizing efficient compute like fly.io, managing connections with PgBouncer, and leveraging durable execution like Trigger.dev decisions that allow you to actually survive the journey to 1,000 users. You are building a foundation that is resilient enough to endure growth, not a fragile, over-engineered glass castle built on Hacker News hype.
I love that synthesis. It's about survival first, scale second. And I want to leave the listener with a final provocative thought to chew on as you go back to your code editors. What if the key to massive scale isn't actually writing perfect, elegant code, but writing code that is perfectly easy to delete? Think about your current code base right now. If you had to swap out your Postgres database for Turso, or change your background queue from Inngest to Trigger.dev tomorrow, how deeply is that technology tangled into your core business logic? The best architectures, the ones that actually compound in your favor, allow you to cleanly rip out an obsolete component without rewriting the entire application. Thanks for listening. The next episode is right around the corner. You can find nifty slides about this episode and a transcript on vibecodersmanual.com. Keep coding to turn Vibe revenue into real revenue.